Greetings and welcome to Make Programming Fun Again. This is the 7th installment of the Crafting Interpreters series. In this series we read the book Crafting Interpreters by Robert Nystrom, and we build an interpreter for the LOX programming language using Go. In the previous episodes we have written a tokenizer and a parser. In this video we can start trying to wire the parser together with the interpreter and at least try and print an abstract syntax tree. And in the next chapter we're going to be looking into actually interpreting that syntax as code. Now there are some things I should have implemented differently. For example, this expression struct. So we have implemented expression as a generic interface, implementing the so-called visitor design pattern. And according to my research, sadly this visitor pattern is not really feasible in Go. So we're basically going to have to get rid of all of this visitor stuff. And we're going to have to get rid of these type annotations, these generic type annotations, like so. So what we can do is we can just run we can do a replace, search and replace using Go's, using Vim's regular expressions like this. So I'm basically going to replace anything in square brackets. So this is a generic, this is a generic, this is a generic, this is a generic, and this is a generic, this, and this. Now we can no longer define the expression interface using the visitor pattern because we are not going to be using the visitor pattern anymore. And what I decided to do instead is I'm just going to define the expression as an interface that can be converted to a string, and we're going to try. I think I'm basically going to implement everything else using pattern matching. Like we will be matching on expression types and so on. It's not going to be very clean, but I don't think we can really do a visitor pattern in Go. And at this point, the interpreter does no longer compile, because in the file AST printer we are using these expression types. So what I'm going to do is I'm going to rewrite the AST printer using, you know what? We do not really have to implement this as a class. What we can do is basically we can do it as a function like debug AST, like so. And it's going to take an expression which is going to be of type expression. And it's going to... No, we don't even have to do this. We can just implement the expression, this stringer. We can basically just implement the stringer interface on expression, like so. And well, okay, we're going to need this helper function, except that it's no longer going to be a method on the AST printer interface, and it's no longer going to take a generic argument. And in line 12 we're going to have to replace it with expr string, which is because we can no longer call the visitor pattern. We can no longer call the accept method on an expression. And yes, so okay, we can now define the string method on a binary expression first. So E is going to be a binary, and the function string returning a string, and it's going to be returning parenthesize, expression operator like sim, and then expression left and expression right, and then on the grouping expression grouping string we're going to return parenthesize group and expression, like so. And then on literal expressions, literal string we can okay, if expression value is nil, we return nil, the string nil, and then okay, so we can do something like this. Switch expression values type. In case it's a string, we can do it like so, fmt sprintf, and we're going to use the q format string. I think this what this does is it basically returns the string the way it would be written as a Go literal, and we're basically just going to pass it as a string. I think like so it should work. And then if it's anything else, we can just return it as fmt sprintf value, and that should, I think that should work. We will see later on. And then visit unary expression func unary string return parenthesize expression operator lexeme and expression right, and then we can delete all of this. And now let's see if this compiles. No, it doesn't compile because parser is still relying on these literal expressions. So we can try then search and replace. We replace this, 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 and we do not replace any of those because they are not generics, they are indices. So now, okay, now it looks like it's going to actually work. And when we go back to the book, I think what's going to happen is, so I think we went all the way up to, we read all the way up to this point, and we have not implemented this synchronized method because the book says it's going to take a while until this is actually going to be used. So what I'm going to do is I'm going to implement this method in our parser. I'm going to implement this method in the parser, and then at some point we'll probably see why it's necessary. Because I think it's going to be easier to just implement it now than have to go back to this point in the book later. So p advance for not p is at end. If p previous token type equals semicolon, we can return switch p peak token type. Okay, so if it's class a function var for if while print return, we return and otherwise we advance. So I'm not entirely sure what this is supposed to do, and the Go compiler is going to shout at us for not using it, and I wonder if we can actually like make it spread it on more lines. I think we can. So I'm going to replace every space in here with a new line. Okay, like so. Okay, this doesn't look too bad. I'm not exactly sure how it's supposed to work, but we'll see. So what it says, with recursive descent, the parser state, which rules it is in the middle of recognizing, is not stored explicitly in fields. Instead, we use Java's own call stack to track what the parser is doing. Each rule in the middle of being parsed is a call frame on the stack. In order to reset that state, we need to clear out those call frames. The natural way to do that in Java is exceptions. When we want to synchronize, we throw that parseError object. Higher up in the method for the grammar rule we are synchronizing to will catch it. Since we synchronize on statement boundaries, we'll catch the exception there. After the exception is caught, the parser is in the right state. All that's left is to synchronize the tokens. Okay, so this describes a way this is done in Java. Since we are writing this in Go, which doesn't have exceptions, we're going to have to handle this parser state using errors, and we're going to be returning those errors somewhere, and we're going to be handling them somewhere in the code. And at this point, it's not implemented yet, and we are not going to use the synchronized method yet, and I don't know when exactly we're going to use it, but we are going to use it. We want to discard tokens until we write at the beginning of the next statement. That boundary is pretty easy to spot. It's one of the main reasons we picked it. After a semicolon, we're probably finished with a statement. Most statements start with a keyword, for, if, return, var, etc. When the next token is any of those, we're probably about to start a statement. I say probably because we could hit a semicolon separating clauses in a for loop. Our synchronization isn't perfect, but that's okay. We've already reported the first error precisely, so everything after that is kind of best effort. Okay. So this method discards tokens until it thinks it has found a statement boundary. After catching a parse error, we'll call this, and then we are hopefully back in sync. When it works well, we have discarded tokens that would have likely caused cascaded errors anyway, and now we can parse the rest of the file starting at the next statement. Alas, we don't get to see this method in action since we don't have statements yet. We'll get to that in a couple of chapters. For now, if an error occurs, we'll panic and unwind all the way to the top and stop parsing. Since we can parse only a single expression anyway, that's no big loss. Also, I'm not going to be using panic because because panic is a very slow way of handling exceptions. We can be pretty sure that while parsing, we can just return errors and then handle them somehow. So we basically just have to see how all of this turns out. Okay, wiring up the parser. Okay. So, okay, in primary, how do we... Okay, but okay, so in primary we can just return nil, and how do we return those parser errors? Parse error. So token is going to be p peak, and the message is going to be expected expression, like so. So we do not need this panic anymore. Okay. And with that, all that remains in the parser is to define an initial method to kick it off. That method is called naturally enough parse. Parser Java. Do we have like a parse method? Func p parser parse, and it's going to return an expression or error p expression. Okay, we'll see if how this we'll revisit this method later when we add statements to the language. For now, it parses a single expression and returns it. We also have some temporary code to exit out of panic mode. Syntax error recovery is the parser's job, so we don't want the parse error exception to escape into the rest of the interpreter. When a syntax error does occur, this method returns null. That's okay. The parser promises not to crash or hang on invalid syntax, but it doesn't promise to return a usable syntax tree if an error is found. As soon as the parser reports an error, head error gets set and subsequent phases are skipped. Okay, do we have a head error in here? I don't think we have. Finally, we can, do we have a head error in, yeah, we do have a head error in logs, okay. Finally, we can hook up our brand new parser to the main logs class and try it out. We still don't have an interpreter, so for now we'll parse to a syntax tree and then use the ASTPrinter class from the last chapter to display it. Okay. Delete the old code to print the scan tokens and replace it with this. Okay, so in run, okay. In the run, what do they have in run? We have scan tokens. We keep scan tokens. Okay, so tokens parser equals parser new parser with the VM and with the pointer to the logs instance and with scanners tokens. Okay, and this is expecting we are actually expecting the tokens to be pointers, and this could actually make sense in this parser as well. So I'm going to replace this with a pointer, and we are going to get, okay, and this should be also a pointer, like so, declared and not used. So then expression and error is going to be parser parse. If error is not nil, we return. So I don't think we're going to actually use this head error thing because we are actually going to return the error. So it may be possible that we're not going to use it. but we'll see. So we return. Yeah, we'll see how this turns out. I'm not exactly sure what the plan is. If we had an error, we return, and then we are going to go fmt print f. No, just print ln expression string, and let's see how this turns out for us. Cannot use p tokens as token value in return statement. Okay, parser.go 230. And we are going to return a pointer and a pointer. And this is probably going to trigger a lot of different tokens. Okay, parser go 53. So we're going to define this to use a pointer to a token, and this is going to use a pointer to a token. And then peak 181. And parse error is also going to return a pointer. Okay, and 222. This is also going to return a pointer. And then in line 200, we no longer have to return a reference like this. Okay, so now 2 plus 2. And 2 plus 2 divided by 2. Yeah, so we actually got to proper parsing of arithmetic statements, and if we give it like a string, it returns a string. If it's a return, we're not doing anything. If it's like a foo plus bar, yeah, I think the parser works fine. The AST printer also works fine. Okay, so it's back to the book. Congratulations, you have crossed the threshold. This really is all there is to handwriting a parser. We'll extend the grammar in later chapters with assignments, statements, and other stuff, but none of that is any more complex than the binary operators we tackled here. It is possible to define a more complex grammar than loxes that's difficult to parse using recursive descent. Predictive parsing gets tricky when you may need to look ahead a large number of tokens to figure out what you're sitting on. In practice, most languages are designed to avoid that. Even in cases where they aren't, you can usually hack around it without too much pain. If you can parse C++ using recursive descent, which many C++ compilers do, you can parse anything. This is a reference to the fact that C++ has an overcomplicated grammar. Okay. Fire up the interpreter and type in some expressions. See how it handles precedence and associativity correctly. Not bad for less than 200 lines of code. Challenges. In C, a block is a statement form that allows you to pack a series of statements where a single one is expected. The comma operator is an analogous syntax for expressions. A comma-separated series of expressions can be given where a single expression is expected, except inside a function called argument list. At runtime, the comma operator evaluates the left operand and discards the result. Then it evaluates and returns the right operand. Okay, I'm not going to do any of these exercises. Also, I didn't know about this really. I mean, I know you can do this, but I didn't know you could do this. Ternary operator, error productions, okay. Design note, logic versus history. Let's say we decide to add bitwise and or operators to logs. Where should we put them in the precedence hierarchy? C and most languages that follow in C's footsteps place them below equals. This is widely considered a mistake because it means common operations like testing a flag require parentheses. If flags, okay, this is wrong, and should we fix this for logs and put bitwise operators higher up the precedence table than C does? There are two strategies we can take. You almost never want to use the result of an equals expression as the operand to a bitwise operator. By making bitwise bind tighter, users don't need to parenthesize as often. So if we do that and users assume the precedence is chosen logically to minimize parentheses, we're likely to infer it correctly. This kind of internal consistency makes the language easier to learn because there are fewer edge cases and exceptions users have to stumble into and then correct. That's good because before users can use our language, they have to load all of that syntax and semantics into their heads. A simple, more rational language makes sense, but for many users, there is an even faster shortcut to getting our language's ideas into their wetware. Use concepts they already know. Also, nice word for wetware. Wetware, I think this just assumes that the brain, this is a pun on the idea that the brain is basically mostly water. So for many users, there is an even faster shortcut to getting our language's ideas into their wetware. Use concepts they already know. Many newcomers to our language will be coming from some other language or languages. If our language uses some of the same syntax or semantics as those, there is much less for the user to learn and unlearn. This is particularly helpful with syntax. You may not remember it well today, but way back when you learned your very first programming language, code probably looked alien and unapproachable. Only through painstaking effort did you learn to read and accept it. If you design a novel syntax for your new language, you force users to start that process all over again. Taking advantage of what users already know is one of the most powerful tools you can use to ease adoption of your language. It's almost impossible to overestimate how valuable this is, but it faces you with a nasty problem. What happens when the thing that the users all know kind of sucks? C's bitwise operator precedence is a mistake that doesn't make sense, but it's a familiar mistake that millions have already gotten used to and learned to live with. Do you stay true to your language's own internal logic and ignore history? Do you start from a blank slate and first principles? Or do you weave your language into the rich tapestry of programming history and give your users a leg up by starting from something they already know? There is no perfect answer here, only trade-offs. You and I are obviously biased towards liking novel languages, so our natural inclination is to burn the history books and start our own story. In practice, it's often better to make the most of what users already know. Getting them to come to your language requires a big leap. The smaller you can make that chasm, the more people will be willing to cross it. But you can't always stick to history, or your language won't have anything new and compelling to give people a reason to jump over. Okay, and we finished chapter 6 about parsing, and I think it's enough for today. I'm not going to be reading the next chapter because it's going to be much more complicated than this one. So I'm going to call this a video. I know this series is not particularly popular with newcomers, but there are a few people who keep asking me about these videos, so I'm going to keep making them. And if you have enjoyed this video, you may consider liking it, and you may also consider joining the waiting list on for my Discord server. which doesn't exist yet, but I will create one once we hit 100 people signing up. So thank you for watching. I hope you learned something, and I will see you in the next episode. Thank you.